Great. Okay. All right, Alex, and the screen is yours.
Okay, thank you. I'll try to share screen. It says sharing is not turned on. I'll click send request. See if this works.
Yeah, I forgot to do that. Yeah.
No problem.
Now, I think we're good to go.
Okay. Hopefully you can see a PowerPoint slide.
Yep.
Super. Okay. Well, yeah, thank you. Thanks to Professor Yuding for inviting me to speak. I also want to say thanks to my colleague Sam, who's on the call. Sam helped me complete the work for this, and yeah, very happy to present the calculations we did on the WeDoWind dataset. The title of the presentation is Wind Up, an open source tool to assess yield uplift of wind turbines. So we're also sharing, we have shared the code used. It's called the Wind Up tool, and I'll give some more details about that during the presentation. I've got, I think it's 14 or so slides broken out down into the motivation for, why do we calculate uplift and why do we make it an open source tool? Most of the slides are about what the tool does, so the analysis method of the tool, which we think is pretty innovative and helpful. Finally, the example calculations show the work that we've done with the WeDoWind data. And I'll close with a summary slide. And go ahead and ask questions during the slides if you want, but I think I've tried to aim for 20 to 30 minutes, so we have time for discussion at the end as well. But do feel free to ask questions if anything's unclear. So starting with the motivation, accurate AEP uplift, that's annual energy production uplift, is a crucial capability in the development of technologies which increase wind farm output. And just a couple of pictures on the right-hand side of some technologies that RES offer, like vortex generators on blades and wake steering control and other interesting control methods. But we don't always have a high-quality wind measurement like a LiDAR. So we need a method which can use other wind turbines as references. So when thinking about this method, I started by reading IEC 61400-12-1 again, which is the power performance measurement standard, and tried to keep the method as close as possible with this standard, but we need some deviations. So one big one is that we want to measure uplift under all conditions, including waked data. And another part where we enhanced it was the uncertainty calculation needs to deal with quite a lot more noise when you're using other wind turbines as references. Overall, it's really important for the wind industry to achieve consensus on how to measure uplift, including the uncertainty of the measurement and how to extrapolate it to long term. Therefore, we made the code, and the examples I'm presenting today as well are all available in a tool called Wind Up, which is on GitHub. So overview of the analysis method. At the core of it, the idea is to define two power curves, a baseline before the upgrade and a post after the upgrade. And the uplift is the change in the energy yield that you can calculate from the two power curves. Not sure if you can see my mouse cursor, actually. Can people see my mouse cursor if here I'm pointing at baseline and post? Can you see my mouse as I move it around or not?
Yeah, you can see
that.
Yeah,
we can see it. Yeah.
Okay, great. I might indicate things with that. So when we're doing this measurement, the y-axis that's pretty easy. That's just the test turbine's power. Normally, you can just simply take what's in the SCADA data and use it. Whereas the x-axis is much more difficult and complicated. So the x-axis, we're trying to estimate the baseline, as in the pre-upgrade wind speed at the test turbine. And emphasis on baseline, because if you're doing something like wake steering, then the whole point of the upgrade is to actually make certain turbines windier, to make those locations, have less wakes, therefore be windier. So that's the whole goal of that. That's what most of the tool is about, is creating this x-axis variable. And this estimate cannot directly use measurements from the test turbine itself, because the test turbine's own, for example, nacelle anemometer could be biased from the upgrade. So ideally, we do have a wind speed estimate based on a high quality nearby wind measurement consistent with 61400-12-1. But otherwise, it's possible to construct this wind speed from surrounding reference turbines. And actually, with the WeDoWind dataset, my first thought was to use the mast, just use the mast wind speeds and don't even use the reference wind turbine. But I ran into some problems with that particular dataset, which I'll explain later on, and ended up relying quite a lot on the reference turbine to create this x-axis variable in the WeDoWind dataset. So a little bit more about side-by-side turbine assessment. I think a lot of this will be familiar to people on the call, but I'll go through it anyways. It's quite commonplace to use reference turbines. In this example, T2 is a reference turbine, which is not upgraded to assess the uplift of an upgraded turbine, which is T1 in this picture. The wind direction as well as wind speed data can be coming from the reference wind turbine. So accurate northing of the turbine's direction data is crucial in the wind-up tool. For some upgrades, and this is the case in both of the WeDoWind examples, we have to do a before and after test. So if you think of time as the horizontal here, we have T2, the reference turbine, being the same throughout the entire time. We're running to compare baseline or before with an after data set. We like toggle tests where we can do that though. So if you have a software or controller upgrade, you can turn the upgrade on and off at short intervals, and that builds greatly reduces your risk of bias due to things like the reference turbine changes over time in ways that you don't have knowledge of. Or there's a general category of bias which I call weather unfairness. So you might have had a lot more stable conditions, or higher temperatures, or different air density or whatever have you. By toggling, you make the weather much more equal for the two data sets. In terms of planning a campaign and choosing references, I've got some thoughts here on how it's best to do that based on our experience. So generally speaking, we want to ensure that any given test turbine has at least 3 nearby references. I like to use 3 references because then if one of the references is drifting, you can use the other 2 to identify that drift. You also want to share wake-free locations fairly equally between the test and reference turbines, because wake-free data is the most valuable data. It's the lowest noise data you generally get. So if you follow these guidelines, here's an 11 turbine wind farm. You can generally upgrade about half of the turbines for the validation campaign. And then, of course, if the campaign goes well, then you upgrade the rest of them at the end. And of course, if you can toggle the upgrade, the risk of bias reduces. So in that case, the number of references can arguably be reduced as well. And more concerns are present for things like wake steering, where you're really concerned about the wake interactions between turbines. So I would say this sort of approach is probably good for like a pitch angle or vortex generator upgrade, but things like wake steering need more thought. So once you've chosen your test and reference turbines and you're gathering data for your campaign, then you can start using the wind-up tool to assess the data. I said earlier on, the wind-up tool is all about measuring power curves, and the Y variable is pretty easy, it's power, but the X variable is very difficult. So that is a wind speed signal, which is mainly derived from the power of nearby reference wind turbines. And how we do that in the wind-up tool is in the middle of the power curve, where power is rising steeply with wind speed. Power is a very good indication of how windy it is. So for that data, we transform the power signal in kilowatts to a wind speed signal in meters per second, basically by doing an inverse lookup on the site average power curve, which has also been computed by windup. However, when you get close to zero power, or when you get up to rated power, the power signal is no longer a good indication of how windy it is. So if you're measuring rated power, then all you know is that it is rather windy, but you don't know whether it's 15 meters per second or 20 meters per second. So for those timestamps, we use the turbine anemometer to estimate how windy it is. And in between, we blend the two. So where it's green on this plot, we're blending the power-based estimate and the wind speed-based estimate. So this all gets blended together into one wind speed estimate, which is used in all upstream analysis. Another innovation in the windup tool is translating the wind speed from the reference turbine location to the test turbine location by defining a directional lookup based on past data. We call this process overall directional detrending. If anyone on the call is familiar with the site calibration part of the IEC power performance standard, it's quite a similar idea. You basically measure the ratio of wind speeds between the test and the reference, which is the y-axis here. And you study that ratio as a function of direction, which is the x-axis on this plot. So in this plot, immediately you can see wake-like details. I'll go to the next slide, which blows this up. So for example, this plot was made from a real wind farm. And at direction 150, there's quite an obvious wake in this plot. And that's actually T14 waking the test turbine. So for direction 150, the test turbine is much less windy than the reference turbine. So we get a very low ratio at that direction. So this directional detrending allows us to correct wind speeds for known wake effects and use all the directions if we want to. And then another nice thing the windup tool does is it computes this process for every availability scenario as well. So it recomputes the data. For example, if you look at 150, there's a second line which represents all the data when turbine T14 is off. And of course, when turbine T14 is off, it's no longer making a wake. So you can see that the wake disappears in this plot. So it's very crucial to account for the time series waking status of surrounding wind turbines to your test turbine and your reference turbine. Because if you don't know about these changes in waking state, this here is a 20% wind speed change, which is going to be something like 50% power change for the test turbine. So even 1 or 2 hours of data with that huge change can easily overwhelm the 1 or 2% uplift that you're attempting to measure. But luckily, the windup tool can do all of this automatically as long as you provide the SCADA data for all of the turbines and provide their lat-long coordinates. Then the windup tool can do all this. And then this is the final slide about methodology, which is uncertainty. So uplift uncertainty is estimated in multiple ways in windup and then combined. The most familiar estimate method it does is quite similar to the 61400-12-1 category A uncertainty calculation, which is basically taking the standard error measured in each bin of the power curve and then aggregating that. So that method is fine, but we found that in a number of cases with turbine side-by-side analysis, that method greatly underestimates the uncertainty, or well, greatly fails to produce an uncertainty, which is high enough, I suppose, is a way to say it. So we've enhanced the uncertainty calculation by adding block bootstrapping, where the data is resampled many times with replacement, which gives you a distribution of uplifts using different subsets of the data. And basically the width of the distribution is another estimate of the uncertainty. We also do a reversed analysis where the roles of the test and references are swapped And so, for example, if you had an analysis where the test turbine has gotten 3% better, if you swap the labels test and reference and rerun the analysis, you should get the answer -3%. But actually, that often doesn't happen. So, and that reveals biases in the data combination of the data and method, which once they're identified, you can simply increase the uncertainty and adjust the answer to account for those biases that this process discovers. The overall uncertainty of a test turbine can be reduced by taking multiple references around the test turbine and combining the answers if the errors from those answers are not correlated. So that's something we often do to drive uncertainty down in a real field campaign. So that's everything on the method. Like the next thing I was going to go into were the WeDoWind calculations. Again, happy to answer questions as we go along. So if anyone has a question, please feel free to ask. But yeah, we can have discussion at the end as well. So the following slides, I think I have 3 slides coming up about the WeDoWind turbine performance quantification data sets. We've calculated the uplift for the 2 upgrade data sets. Each data set includes a mast, a test turbine, and a reference turbine. I think we've named the 2 data sets VG and pitch angle. So the VG or vortex generator data set is about 14 months worth of data before the upgrade and about 8 weeks of data after the vortex generators were installed. And then there's the pitch angle data set, which is a neat artificially created data set with about 8 months before and 8.5 weeks after. So I want to say thank you again to Professor Yuding and the WeDoWind team for sharing the data and facilitating the collaboration. It's always great to be able to, have a challenge on some interesting data and to compare approaches using the same data in a bigger community. So the first one I'm showing is the VG example. Just cutting straight to the answer, we think the AEP uplift is about 2.3%, and the uncertainty is reasonably good. So in this table down here, I'm showing a 90% confidence interval, and I remember the 1 sigma uncertainty is only about 0.5%. So even the P95 is quite a strong uplift. The wind-up tool produces the 4 plots you see here on the right. So maybe going to the 2 bottom ones, these 2 bottom plots show the distribution of uplift versus wind speed. The bottom right plot is percentage uplift, so this is probably the easiest one to understand. It's showing 0% uplift measured up to about 8 meters per second. And then the uplift is pretty strong, up to 4 to 6% uplift in those wind speed bins. And then from 12 meters per second onwards, it's outputting 0 uplift. The plot to the left is the same information again, just cast as megawatt hours using the frequency distribution derived from the data. The uplift is, well, I would say the data count is quite low at high wind speeds. You can see from the scatter plot that the knee and rated power regions are not very well populated. So probably the true uplift answer is different, because the wind-up tool sort of resorts to saying 0 uplift in wind speed bins where it cannot do the measurement. So ideally, you let the measurement campaign go on for longer. My impression, this is an 8-week post-upgrade data set, and normally when res do upgrades like this, we have at least, say, 4 months post-upgrade and sometimes longer. But overall, this is a nice data set to analyze. We've got well over 300 hours pre and post, which is not bad. And the script that creates these plots is available in the windup repo in the examples folder if you want to run it yourself.
Alex, can I ask you a quick question here?
Certainly, yep, go for it.
Yeah, is the 2.3% is only the test turbine alone is relative to the control turbine. So if you apply your method to the control turbine itself without accounting for the test turbine, do you see a kind of a positive value, however small that is?
Yeah, that's a good question. So, yeah, actually, in this analysis, I just assumed that the reference or control turbine had no change. Because I found in order to check the reference turbine, we'd have to use the mast alone as a reference. And I did not try an analysis where I just used the mast data. But that would be a good thing to try. I'll show a few more plots later about why it was a
Well,
little
the
bit.
reason I'm asking that is I looked at our own paper, analyzed the same set of data published in 2021. We actually got almost exactly the same answer as you do here. Our estimate for the VG turbine is 2.29%.
Yeah.
The final number we report is 1.34%, because if we apply the same analysis to the control turbine comes with 0.9 some percent. And so
Yeah.
we take the difference, we said relative to the control turbine, because there's always a bias aspect. You cannot guarantee your data analysis is entirely bias free. And so, but interesting to see the kind of analysis you produce and we did previously agreed with so closely with each other.
Yeah, that's always a good sign.
Yeah.
But I agree. This is the worst part about using other turbines as references. You just never know if they're drifting. So yeah, we'll call it a solution for that problem is this advice that take 3 reference turbines, and that way you can check each reference turbine against 2 others. And if one of the references, at least you can rule out the one which is different to the other 2 if they're not all stable. Because I mean, at the end of the day, you never really know if your reference turbines are drifting or not, no matter how many you take. So I think using the mast would have been preferable here, but I didn't want to use the mast on its own either because I have so little information about the mast. But
yeah, sounds good. Go ahead.
Yeah, I guess. But yeah, I guess the answer to your question is I do not have a uplift measurement of the control turbine or reference turbine. I just had to trust that it was not drifting. And yeah, I can definitely believe that you might look at it and say, "Oh, it's 1% different." That's not an unusual thing to find on turbines which are supposedly unchanged.
Right. Yeah. So if you have time, if you could just apply your analysis to the control turbine, use the master's reference, and it might produce a similar result, right? For this particular data, we don't really know the underlying truth because the data was provided by one owner operator, and they have their own internal analysis result, and but it's impossible to do the physical experiment and to exactly know what is the underlying truth. So the different group come up with their own estimate in a kind of a range. If I don't remember wrong, the owner operator's internal estimate is a little bit kind of less than 2%. And I don't remember the full history of that. And that's probably one of the reasons after we did our own analysis, we take the difference between the VG turbine and the control turbine, which is getting closer to their own estimate. But they didn't really disclose how they did their analysis. So we don't really know. We only know a rough number, what they got. Yeah. There's no guarantee they are right either.
Yeah, this stuff is definitely difficult. Like what you really want to do is install your VGs, let the turbine operate for a year, then put the turbine in a time machine, send it back in time a year, take the VGs off, let it operate again for that year. That's what you need to do to really know the true answer, but you can't do that. So
exactly.
But yeah, I think generally speaking at res, if we clear like the P95 is greater than 0 hurdle, then at least we're feeling happy that we've genuinely made the turbine better. But yeah, there's always going to be a spread, and like once you then roll the upgrade out to the rest of the turbines on the wind farm, they will probably get some higher, some lower results. So
That's right.
yeah,
Right.
value.
I do get the same feedback from the vice president responsible for the asset management for that particular wind company, and he said he understands there's a kind of uncertainty with your final estimate. Therefore, for his decision to go ahead with this kind of upgrade is really it's going to be positive or negative, right? If you have the 95% or even higher confidence, it's going to be positive. They believe it's going to worsen. But it's a negative, better not to do it. So exactly like what you said.
Oh, nice. Okay. Yeah, that makes
Yeah.
sense. Right. I'll show the second analysis. So this is the pitch angle one. So this is a neat data set where power was multiplied by 1.05 for wind speeds above 9 for the post part. And you can see that in the power curves straight away in the scatter plot. You can see the post upgrade is clearly higher than the blue for 9 meters per second and above, especially at rated power. It's easy to see. And you can see that in the binned power curve quite easily too. So for this one, I guess we were expecting results to be 5%, and in the bottom right, I was pretty happy with how this looks. It is definitely noisy, but I've kind of drawn on the expectations over the plot that Windup produces. So we were expecting 0% uplifts up below 9 meters per second, which it's pretty much in line with expectations. And then from 9 meters per second up, we were expecting 5%, which is not perfect fit, but it's looking good. It's looking consistent with where it should be. So yeah, overall, when you convert that power, when you multiply this through the frequency distribution to turn it into an AEP, then that turns out to be a 3% figure. And the uncertainty is not bad. It's a little bit worse than the previous example, of reasons I can explain on the next slide. But yeah, overall, Windup handles this case fine, I think.
So Alex, actually, your estimate is pretty accurate. You know, the multiply 0.5 is 5%, but only for a subset of the wind speed. We actually calculated the equivalent improvement of the power. You just add all the powers together and compare with the change before. The equivalent is 3.11%. So you got 3.0% is you know, it's within 5% difference between your estimate and the actual. For this one, because it's simulated, so we know the underlying truth.
Yeah, definitely making artificial data sets like this where you know the answer. This is a great way to test methods and tools. So yeah, that's nice to have an expectation that you can compare your results to.
Right. So one of the things, if you are interested enough to do, is you know, for the simulated data, we actually give a spectrum of the different kind of improvement, right? The 5% is one of the numbers being multiplied. There's also from 2%, 3%, 4%, all the way to 9%. So the equivalent of the actual power improvement is range from 1.25% to 5.6%. So some of the method does better job in the mid body of that range. Some do better than the high end. Some does better. Usually the harder one is the smaller percentage because of the noise issue.
Yeah, that makes sense. Yeah.
Right.
I think I have one more slide on We Do Wind. Yeah, so I guess if for me working on like a lot of commercial wind farms, I had some I guess comments or ideas if we do if there's another exercise like this. And you know, these might be things that RES could help with in future if we want to make more data sets like this. So for the Windup tool, there was some, if you look at the example on GitHub, there there's some things that Sam and I needed to do to get Windup to run, basically making up for data that's missing. So for example, lat longs of all the objects, turbines, and masts are very valuable in the Windup method because Windup computes the waking relationships between things, and then data for all the nearby turbines as well. So my understanding is this was your inland wind farm, which in reality has many turbines, but I guess we don't have access to data for all the turbines. So there could be basically neighboring turbines creating wakes, or maybe not creating wakes when they're offline, but we don't have information about that. So when we have that information, Windup can use it to discriminate between this turbine is waked in this timestamp versus this turbine is not waked in that timestamp, and use the data differently. And Windup also likes more fields, so especially pitch and RPM, and the wind speed of the turbines, of course, because those are quite useful for filtering as sort of, probably on older wind farms, it's not so much of a problem, but on newer wind farms, wind turbines do many more complicated things like grid curtailment, noise curtailment. They might do power boosting in certain situations. And the pitch and RPM data is very useful because it helps you understand what the turbine's intentions are. So yeah, due to missing information, in my analysis, I did quite a lot of directional filtering just to avoid bias due to wakes. So for example, I was like the mass data, I did something quite just because of lack of time. I took a very simple approach to it. I quickly calculated the CP, the coefficient of power that the mass data implied, plotted that versus direction, and I could see that probably in these sectors where the CP goes unrealistically high, probably that's the mast being in a wake of a nearby turbine, but I'm not actually sure because I don't have the lat longs. So how I handled that is I just simply just got rid of data where the CP versus direction relationship looked different. So for example, in the VG analysis one, I think most of the data was filtered out apart from like the south and southwesterly data. So there's a little bit of heavy-handed filtering when you don't have stuff like lat longs and pitch and RPM, which that would allow for more informed filtering, so you could keep more data, if that makes sense. Another reaction to it, so the pitch angle example is interesting because it was a rated power boost. So actually I don't see tons of rated power upgrades in the field. So that was actually nice because I could, at first the Windup tool didn't handle that situation that well. So it was a nice opportunity to improve the tool to handle rated power boost. And then the final one, which was a little bit different to the usual assessment, is that the pitch angle data set, I think, is something like 12 months in total, but the last 8 weeks are the upgrade. So I think the upgrade, here's the month of year distribution. I think the upgrade data is mainly in May and June, but because the total length of the data set's 12 months, you don't have May and June from the year before. So as a compromise, I just used August and September mostly from the year before. So it's close to seasonally matched, but it's not quite. And actually in this analysis, I did not use any data from the winter at all because I was worried about the threat of weather bias, basically. So I just didn't use winter data.
Right. So Alex, I like to comment on the data part issue. The data are relatively old, was obtained roughly about 10 years ago. The pitch angle, because it's simulated data, is possible at that time to simulate the whole year after the change, right? I believe at the time we do have not many data points. The reason was only simulated 8 months. 8 weeks is because of the actual VG upgrade data was provided by the operator. They only give us 8 weeks. We just want to match whatever that duration at that time. And now afterwards, after so many years, and then it's very hard to kind of align the data to say where the data originally come from anymore. On a different note, we did another analysis with wind energy of Institute of Canada 2 years ago, and that was 4 or 5 different turbines and multiple year data. And there are some always decision point, so you can delineate the before and after change. There are also kind of continue running the monitoring things, but they do have much longer duration of the data. And they just allowed us to release that set of data earlier this year. After we started, we do wind part. So the data right now is on my website, wherever people can find those the current VG and the pitch angle upgrade data. They can find the other set of data. I plan to ask my PhD student at a later stage, if it's not October, probably November, to kind of give a presentation, explain the type of study we did over there, and that set of data, probably provide a link, and people, if like yourself are interested, can analyze that set of data. That data is much bigger. It's almost like 300 megabytes data being released, roughly about the early June to mid-June time, when they give us the go ahead, right? And another thing is from all the participants on this collaboration, we from university, we don't really have data per se, right? The owner operators, they have data. So I actually want to take this opportunity to say, if you guys have the data, can be used as a good example to support this kind of things, and sharing the data is one of the purposes to do this collaboration.
Nice. Yeah, that makes sense. Yeah, I look forward to seeing the new data. That sounds good. And yeah, it's on my mind that I would like, I think Res has some data that could be shared openly as well. So that would be, I'd be happy to discuss that in future, how to go about that. Because yeah, open data is very valuable.
Alex, just from my side of that topic, I would like to pick up with you on that topic, maybe separately, because there are also other topics, challenges that look at with data. And if you think it's a possibility to get data sets for this overall project, we should talk.
Yeah, I'd be happy to, Sarah. Yeah, sounds good.
Great, thank you.
But yeah, well, thank you, Professor Yuding, again, and everybody who made this collaboration possible. I'll just wrap up my slides. So to summarize, we've put out a new innovative method to measure uplift. It's applicable to a variety of upgrades and different reference data options as well, which I didn't go into in this presentation, but yeah, Res do a number of different upgrade services, so we've tried to make the method quite flexible. We've tried it, Sam and I tried it on the WeDoWin datasets, and the results look reasonable. The tool works, it gives, reasonable looking uplift and pretty good uncertainty. And the examples are all on GitHub. Try to just show where they live in this repo. So in this repo, there's a WeDoWind example.py, which creates all of the graphs and more from the presentation just now. And there's also a Python notebook on the SmartTeal example dataset, which is a nice open source wake steering dataset, which might be a good place to start to dig into it. So yeah, that is everything I wanted to share today. Thanks for your attention, and thanks for the invitation again.
Well, thank you very much, Alex. It's a very interesting talk, and I learned quite a lot. And I'm wondering, I asked most of the questions during your talk. I'm wondering if any questions from the audience or any discussion. We have about 15 minutes left.
I have a couple of questions. That's all right. Yeah, thanks a lot for the presentation. It's very, very nice. A couple of points interest me. I think firstly, on the sort of directional detrending, is there a risk that, you talked about times when a certain turbine is offline and measuring the difference there? Is there a risk that in your reference period, you don't have enough data points to determine that different? Because ultimately we're talking about, there's a whole matrix of turbine relationships there. And if there's not enough data in the reference period covering a certain turbine being shut down, but then that occurs in the test period, is that a bit of a risk?
Yeah, thanks for the question, Phil. Yeah, so how the tool deals with that now is it just doesn't include that data. So we saw an example where a third turbine called T14 was either on or off. If the reference period did not have any experience of T14 being offline, but then the upgrade period has loads of data where T14 is offline, then it just doesn't use that data.
Yeah, okay. So there's certain thresholds to meet, and it's sort of automatically excluding data on based on how many samples there have been or something like that. Yeah.
Yeah, there's a setting. Sam helped me use Pydantic models in the windup tools. And there's a setting on the model there's a big object called the windup config, which is the big object that holds all your settings. And it has a default setting called detrend minimum hours, which is 24 hours, which we just took from IEC 61400-12-1. They use 24 hours in the site calibration bin is the bin valid criteria.
Yeah, okay.
You can change that, so you could use 12 hours or something, or even 6 hours if you really want to squeeze as many detrending results out of your data as possible. But yeah, by default, you have to have at least 24 hours for a sort of direction and waking scenario combination.
Yeah.
For it to be included.
Okay. Yeah.
But
yeah, makes sense. Yeah. Okay. My second question is related to uncertainty. I mean, you mentioned a couple of times about seasonal bias, and I think so. I completely agree with you that using sort of standard error of the mean is going to, underestimate uncertainty. But I'm wondering if the bootstrapping also underestimates the uncertainty to a certain extent, because if, for example, so you have a 12-month reference period and then your test period is sort of in summer or something, which is going to change your power to wind speed relationship, then just taking different samples from within that 2-month test period is not going to capture that part of the uncertainty.
yeah, absolutely. I mean, as you well know, bootstrapping can't tell you anything outside of the data you've collected. So yeah, it is definitely a challenge. Like if we're trying to say what the overall AEP is, but we only have summer data, like we have absolutely no data from the winter, bootstrapping can't tell you what that bias is. So I think that the tool can definitely be improved. Like there's not a really rigorous treatment of what you'd call category B uncertainties. That's the terminology in 61400-12-1. So like 61400-12-1 kind of states clearly at the beginning, what you're measuring is the power curve during the weather of your measurement campaign. You're not measuring like a power curve for AEP, unless of course you measure it for 20 years. That's the only way to really do it. So yeah, I think you're right. I think there's a gap. There's potentially a gap or an underestimate in the uncertainty if you don't have good seasonal coverage. That is something that's been on my mind that I'd like to do more work on.
Yeah, there's a technique that I've tried sort of on the reference period of batching and taking batches and seeing what the distribution of those sort of batch means would be. I've presented it at West before, but I'm not sure if I've ever shared that with you or whether you've seen that.
No, I
it-
haven't seen it. Yeah.
yeah, it'd be potentially interesting to get your thoughts on that. I mean, it's technique sort of I came up with, but yeah, always be good to have a second opinion.
Yeah, please share it, Phil. Be happy to chat more about this because, yeah, it's really important. I think, as you probably know as well, there's always commercial pressure to have shorter campaigns for obvious reasons, and that always scares me a bit because you're not getting that seasonally balanced coverage.
Yeah, well, the uncertainty reduces as you have a longer measurement campaign. So yeah, I think it's about what uncertainty you can take. I'm not promising to reduce the uncertainty. In fact, I'm probably promising to increase it, which maybe doesn't help the commercial side.
But
No, I
you
think
first
you're right,
have
yeah.
to measure it accurately, right?
Yeah,
You first have to quantify that accurately.
yeah.
Any other comments and questions? Philip, did you give a talk early this year? Are you one of our guest speakers?
Yeah,
Do you remember?
yeah,
which one?
I talked on wind speed calibration and Nissan
Right.
anemometer calibration, and yeah, doing that with
So-
machine learning. I'm not sure if I talked on this uncertainty quantification.
Okay.
As I said, I given a presentation on at WESC on it.
Okay.
I may have done it in another forum like this one. Yeah, how
I
many
will
times
look
have you had
at-
me speak? Once or twice? I'm not sure. I think
Once.
yeah,
Once.
and I
don't
talked
think-
once in the other one, in the ODE one. Yeah. Mhm.
Right. In this forum, other than myself, I think all the guest speakers only talked once.
Yeah.
And I will look for that particular month when you give the talk and send that information to Alex. If there's a recording, there's slides, Alex, you can take a look of. I don't remember either, Phillips. You talked about the UQ part or not, but
I think that's a different topic that I talked on
different
in this
topic.
space, because it was on anemometer calibration. Yeah.
Right. Yeah, that's what I remember too. Okay.
Yeah, quite similar to 3E's talk recently. Yeah.
Any other questions and comments? Well, I also would like to take this opportunity to see if anyone else had a topic to present in October. It's going to be on October 14th. If you are, and please drop me a note in the next couple of days. If I don't hear anyone from this group, I will assume no speakers for October. I will ask my PhD student present something we've been doing recently, actually follow up some of the topics from the early speakers and do some reanalysis, so to speak. And then probably after that, we like to explain the new set of data, and like I just mentioned, which is available now on the website. Okay. All right. Okay. So great for today's discussion, and hopefully see you all in a month. Thank you. Thank you, Alex, and thank you, everyone.
Thank you.